All right, y'all. So only a couple more things to talk through here, and then you can finish your activity. Okay, so I want to make sure you calculated your energies is around negative 220 kilojoules per mole for each NADH making 1 water. You should get around negative 200 for each FADH2 making 1 water, right? This is the total energy that's released when we do our electron transport. And if the process is 100% efficient, that's how much energy we can then transfer when we make ATP. So the next question then says, how many ATPs can you make? Noting that it takes 30.5 kilojoules per mole to make 1. So you should end up with like 7.35-ish for NADH and like 6.7 for FADH2, right? So if everything's perfect, each FADH will give us 6 ATPs, each NADH will give us 7 ATPs with a little bit of energy left over, okay? That's important. And if you think about the electron transport chain, it really kind of makes sense that the life evolved in a way where NADH pumps more protons and can then yield more ATP because it releases more energy, right? So these systems have evolved in a way to kind of like take advantage of the extra energy that NADH provides when it reduces water, when it reduces oxygen, okay? So we now have to think about the energetics of proton transport across the membrane. And then conversely, proton movement back across the membrane, right? One direction consumes energy, it requires energy. The other direction releases energy. Okay, and it turns out there's really 2 pieces to the equation here. There's 2 pieces of the puzzle. The first one is the concentration gradient. Across the inner membrane of the mitochondria, or the thylakoid membrane if you're talking about plants and chloroplasts, or the plasma membrane if you're talking about bacteria. But across this membrane, there's a low concentration of protons on the inside. There's a high concentration of protons on the outside. So it costs energy to move a proton from the inside to the outside. That cost corresponds to a positive delta G. Okay? Whenever we're dealing with concentrations and delta G, it always ends up being delta G is equal to RT natural log of that ratio, right? Okay, so this one I hope is pretty straightforward. So on the x-axis, we're plotting the concentration ratio, right? So if the higher the concentration on the outside and the lower the concentration on the inside, we'll give a larger ratio. So as this ratio goes up, we see that it requires more energy to move a proton against that gradient. That should make sense. The larger the concentration difference, the more energy it requires to move the proton. We also have to consider the voltage difference across the membrane, right? This is the electrochemical part of it, the electro part of it. Because protons have a positive charge, and we already have established a chemical gradient across the membrane, we also have established a potential gradient, okay? And as it turns out, basically every cell in our body has an electrical gradient across it as well. It's not just the matrix of the mitochondria. And this voltage difference is measured as delta V, okay? And the way that we define the delta V, it means the inside, the place where we are transporting it, is more positive. So a delta V being greater than 0 means that the resulting position is more positive, okay? So for us, as we move it from the matrix to the inner membrane space, having a positive delta V means that the inner membrane space is more positive, the matrix is more negative, okay? And that's exactly what it is. So the idea here is that the larger this potential, the more energy it takes to move a positive charge from a negative space to a positive space, okay? So the same kind of theory applies here. As this membrane potential increases, that means there's a bigger charge difference across the membrane, the more energy it takes to move something that has a positive charge against that charge gradient, okay? Each of these are calculated separately, but we can combine them together in one kind of big piece, and that's this equation. The first part of it is something that should look very familiar to you. Delta G is equal to RT natural log of Q. That's what it is, okay? So C2 is the concentration outside in the inner membrane space. C1 is the concentration inside in the matrix, okay? You can easily calculate the energy it takes to move a proton against its concentration gradient using this part of it. The second part of it takes into account the charge gradient, the membrane potential, okay? Z is the charge of the molecule. It's a proton, so it's +1. F, again, is Faraday's constant, just like you saw. And delta V is going to be the potential of the membrane, okay? And for the inner membrane, the direction we're going, this value is going to be positive. It takes energy to move a proton from the matrix out to the inner membrane space. It takes energy both to oppose the concentration gradient and to oppose the charge gradient, okay? So with this equation, you can calculate how much energy it requires to pump one proton. We know how much energy is supplied by each NADH or each FADH2. That was question 1 on your activity. So we know we can figure out if we're pumping 10 protons, how much energy does it take to pump 10 protons? How much energy does it take to pump 6 protons? Right? And we can then calculate, is there enough energy in reduction of water to power pumping 10 protons? If there is, how much extra, right? Because this is an efficiency thing. If we use exactly the right amount of energy, it's 100% efficient. But if we produce more energy during electron transport than we consume as we pump protons, then it then makes sense that we've lost some energy, right? Some of the energy is lost, and that lost energy is translated into heat, okay? So the rest of your activity, the rest of the time today, is really doing this calculation and thinking about how that then translates into concepts for efficiency of the process, okay?